This is Daniel Coosberry, and in this lecture we're still looking at geometrical properties. In this entire lecture we're going to look at right triangles and what's called trigonometry, which is a math that you can use with right triangles using particular properties of them. So here in this little yellow box we have what we call trigonometric ratios, and they're ratios that apply to any right triangle. So from a particular angle A, so let's just kind of look at this figure first. This is angle A, where I put this little blue mark. We're going to define the sine of angle A, it's called the sine, as the length of the opposite angle, the length of the side opposite angle A, which is this thing right here. So here's angle A, here's the opposite side, divided by the hypotenuse, which is the side that's opposite the right angle. So this is the opposite side of angle A, this is the hypotenuse. If we have those two lengths, we can calculate the side A over C. Similarly, the cosine of angle A is the length of the side adjacent to angle A, which is this thing right here, this B, divided by the length of the hypotenuse, which is right here. So if we have these two sides, we can find the cosine of angle A. And then the tangent is the side opposite A over the side adjacent to A. So this value over this value, you divide those two numbers, you get the tangent of angle A. And these formulas may seem a little weird. I'm going to show you a few examples where you use them, and then hopefully they'll be a little more clear. One mnemonic that's going to help us out is it kind of uses these letters here. So we have sine, we have opposite, we have hypotenuse, we have cosine, adjacent, and hypotenuse, and we have tangent, the opposite, over the adjacent. And that kind of makes for a nice little mnemonic where you have the sine is the opposite over the hypotenuse, the cosine is the adjacent over the hypotenuse, and the tangent is the opposite over the adjacent. We call that SOHCAHTOA. Doesn't really mean anything, but it's not as hard to remember as all these formulas here. SOHCAHTOA. The sine is the opposite over the hypotenuse, the cosine is the adjacent over the hypotenuse, and the tangent is the opposite over the adjacent. So we're going to use SOHCAHTOA on this next thing. I'm going to write it again. SOHCAHTOA. Because now I can kind of remember some things if I can write that out. This asks us to find the sine, the cosine, and the tangent of angle A. So I'm going to do each one of those. The sine of angle A is equal to the opposite over the hypotenuse. And that's going to be the opposite over, so the 6 over the hypotenuse, which is 10. 6 over 10. That's really all I have to do. Opposite over hypotenuse to get the sine of angle A. So I can reduce this as 3 over 5, or I could write it as a decimal if I wanted to, but that's the sine of angle A. So similarly, the cosine of angle A is going to be the adjacent over the hypotenuse. So it's the side adjacent to angle A, this 8, over the hypotenuse, which is still 10. And that's the cosine of angle A. So having kind of numbers on this might help these formulas make a little sense. The tangent of angle A is going to be the opposite over the adjacent, that's the TOA part, which is 6 over 8, which is 3 over 4. So those are the three things. So if I have all three of these side lengths, then I should be able to tell you the sine and the cosine of angle A and of angle B if I wanted to. So that wouldn't be a hard thing to do. So given a right triangle, I can find these three things if I have enough information about the sides of the angle, or the sides of the triangle. Okay, so I can also use these trigonometric functions to find missing pieces of the angle. So not only did the triangle, not only can I just identify what the sine, tangent, and cosine are if I have the lengths, but maybe I don't have this length, but I have this angle here and I have this length. I can actually use these pieces and using trigonometry to find out the length of angle B. Okay, so let's treat angle A as the angle of interest still, and I have some ratios that work. So for example, I guess kind of what I'm getting at is I want to do something with angle A. I want to either use the sine, I want to use the cosine, or I want to use the tangent. of angle A, and I want a formula that involves not only the opposite of angle A, but the adjacent of angle A also. So I have this angle, I know this angle, I want a formula that has the opposite and the adjacent in mind, so that's going to be tangent, tangent's opposite over adjacent. And I'm going to write it like this. I know what angle A is now, so instead of writing an A here, I'm going to write the measure of that angle. Okay, so I couldn't do that back here because I didn't know what the measure of angle A was, so I just wrote A there. It was unknown. But here I know what the measure of angle A here is now. The tangent of the measure of angle A is equal to the opposite over the adjacent, which is 23 yards over B. Okay, so this is still a TOA. I still have a TOA thing going on. I have the tangents equal to the opposite over the adjacent. I know what this is now. I don't know what B is. But this is still true based on the definition of the tangent. Okay, so now I actually have an algebraic expression where I don't know what B is. I want to solve for B, so I'm going to multiply B by on both sides of the equation. And if I do it on the right side, it cancels out. On the left-hand side, I get B times the tangent of 44 is equal to 23. And then I'm going to divide both sides by the tangent of 44. That's just a number. So that cancels on the right side. So then I get B is equal to 23 over the tangent of 44. Okay, now you might think this just looks weird and doesn't make any sense, but this is actually something I can find in the calculator. So I can find the tangent of 44 in the calculator. You want to make sure your calculator is set on degree instead of radian. But if I do the tangent of 44, I get something along the lines of 0.9657 or something like that. So some little number there. So then I can do, or I could do that directly and do 23 in my calculator over the tangent of 44, and I get 23.82 as my length of B. So that's what this is, 23.82. That's not degrees, that's yards. Okay, so again, so what I did was I started with my TOA, tangent equals opposite over adjacent, and that gave me my variable, and then I had to solve for my variable, which got me here, and I used my calculator to kind of finish the job. So these trigonometric functions are pretty useful for finding out parts of triangles that you may or may not know. Okay, I can do the same thing here. I have an angle that I know the measure of, this 30, so this is going to be my angle of interest, and I want to solve for C this time. So starting with angle A, I want a formula that uses the opposite, because I know what that is, and the hypotenuse, because I don't know what that is. So if I have my SOHCAHTOA, I need a formula that uses the opposite and the hypotenuse, which is this first one right here. The sine's equal to opposite over the hypotenuse. So I'm going to write this out. The sine of 30 degrees is equal to the opposite, which is 20, over the hypotenuse, which is C. And now I have something that's really similar to the last problem, but I had to use a different function this time. I used the sine function. The sine of this angle is equal to the opposite over the hypotenuse, which is what that is. So now I'll do the same thing. I'll solve for C like I solved for B in the last one. So I'll start by multiplying both sides times C. Cancels out on the right, and I have C times the sine of 30. It's equal to 20. And then I'll divide both sides by the sine of 30. That cancels out on the left, and I have C is equal to 20 divided by the sine of 30, which I'll do in my calculator. And I end up with 40 as my answer when I just do all that in my calculator. So C is equal to 40 meters. Put the meters there. So these formulas are really useful for finding out missing sides if you need to, or if you just need to identify the sign for some other reason. So now we're going to look at a common application of trigonometry. There's a concept called an angle of elevation or an angle of depression, which you can use to calculate things. So just imagine that you're standing here on this this platform here, and you're looking at things. And if this dot, let me just start with this dotted line. This dotted line is going to represent a line that is parallel to the ground. So just imagine it being a flat line. And then imagine you're looking at this plane overhead that's above the ground or above your line of sight. The angle that's formed by these two lines, the line parallel to the ground and the line going to the plane, is called an angle of elevation. Okay, so let me kind of erase my scribbles. Do you kind of see how this forms a right triangle? So here's a right triangle. There's a right angle here because it's parallel to the ground. So that's straight up. That's parallel to the ground. So it's right angle. This angle here is called the angle of elevation. Okay, similarly, imagine that you're standing up here and you've got this angle parallel to the ground, and instead of looking at the plane, you're looking down at this car, in which case now you have a right triangle down here where the right angle is still right here. And this is called the angle of depression. This is a very, very similar idea. One of them's just called elevation because you're looking up. The other one's called depression. You're looking down. So with either of those, we can actually calculate some interesting things because we can make this imaginary right triangle and use trigonometry, use this angle to find out some things. So here's kind of a common problem. We have at a certain time of day, the angle of elevation of the sun is 40 degrees. So if you're just standing somewhere looking at the sun, the angle of elevation is going to be 40 degrees on a certain time of day. So maybe you just know that. Okay, and then here we have a tree whose shadow at that time of day is 35 feet long. So what happened is we've got a right triangle where the angle of elevation is 40 degrees, and this side is 35 feet, and we can actually use trigonometry to calculate the height of the tree. So this is the thing we don't know. There's that little white h there. So if we wanted to find the white h, we'll use trig. And so this is our angle of interest because we know what the measure is. We know this is 40. So we need a trig function that uses the opposite angle and the opposite side and the adjacent side, which is tangent. The tangent is equal to the opposite over adjacent. Because those are the two things we're interested in. We have this number, so it's interesting. We don't have this, but we want it, so that's also interesting. So we can write this out. The tangent of 40 degrees is equal to the opposite over the adjacent, h over 35. Then we solve for h. So multiply both sides by 35. It cancels out on the right, and you have h is equal to 35 times the tangent of 40, which I can do all that in my calculator. 35 times the tangent of 40 is 29.37 feet. So 29, almost 30 feet. So it's kind of cool. The angle of elevation and knowing the length of the shadow were the only two things we needed to calculate the height of the tree, which was pretty nice, seeing as it may have not been practical to just run a tape measure of the tree or something like that. Okay, here's a similar problem where we have a tower that is 125 feet tall. We just know that. Somebody probably built it and knows how tall it is. And it casts a shadow that's 172 feet long. And then the question is, find the angle of elevation of the sun to the nearest degree. So now we know the height of the tower, and we know the length of this shadow, and we're interested in the angle of elevation, which would be the angle made by this side parallel to the ground and this hypotenuse, which is pointed towards the sun. So it's going to be this angle right here. Let's call that A. This doesn't have a name. And so we'll use trig again. We have this, from this angle, we're interested in the opposite and the adjacent, so that's tangent again. The tangent of angle A is equal to the opposite over the adjacent. So the tangent of angle A, I'm just going to do that division, is equal to like 0.727 or something like that. Okay, now we're in a little challenging spot because we need the angle of the measure of angle A. We need this, and we know what the tangent of angle A. So we're actually going to use what's called the inverse tangent, which on your calculator it's something that looks like this. You should see if you're using the TI-30 or the TI-84 or 83 or something. If you do second tangent, then you should get this function right here. So hit the second button and then hit tangent. You should get this. It should be kind of scribbled on your calculator. And if I do that, that's going to give me the measure of angle A. So the measure of angle A is going to be we'll call that the inverse tangent of 0.727. Which gives me 36.02 or something. And that's going to be the measure of the angle. So that one was a little bit different, but because we needed to find the angle, so I'll kind of talk through it again. We started not knowing what A was, but we had the opposite of the adjacent. That led us to this tangent formula here, T equals O over A. And then when we got down to it, we had the tangent of angle A is equal to a number. To get A, we had to do the inverse tangent of that number, which is on your calculator, second tan. And that's what it took. So the nice thing is we have three formulas, and we use those three formulas for every single one of these problems. And so you do some practice with this, and you kind of figure out which formula you need. And most of them, we just had to do some algebra to solve for like C here, or to solve for B. Here we solved for H or something like that. And then this very last one was a little bit different because we didn't need to solve for a side, we needed to solve for the angle. Now when we solve for the angle, that's when we had to use the inverse tangent. So on your calculator, you'll see there's also inverse sine and there's also inverse cosine. So you'll see if you do second sine, you get something like that. If you do second cosine, you get something like that. And that comes into play when you have problems that look like the cosine of angle B, for example, is equal to 1/2 or something. Then you would do B is equal to the inverse cosine of 1/2. And that'll give you the measure of the angle. So there's kind of two different problems here. But the nice thing is you're still using sine, cosine, or tangent to set these problems up, which is a good way to get you started.